And I was muted. So, okay, we're recording. We are talking about sections 2.4, 2.5, and the focus on theory for chapter 2 this week. So why don't we just jump right into the second derivative? Did you read the chapter, like you said you didn't read it like a bunch of times. Did you kind of like get what was going on conceptually?
Kind of. Like at first I was really confused, and then when I caught up with Kasha's, I just realized the second derivative is nothing more than interpreting if the line is concave up or concave down, increasing, decreasing.
Basically, yeah. So if we're looking at the rate of change of like a function, right, we're looking at its derivative. But if we look at the rate of change of a function, we're looking at its second derivative. So it's basically like, what if we took the derivative of a derivative, which is, you know, in essence what's going on here. So I'm going to sketch out, this is problem 2. It's a little sloppy looking, but in essence, there are a bunch of points here, A, B, C, D, and E. And it's asking you to label the points on the graph where both dy dx and d squared y dx squared are negative. So basically where the first and the second derivative are negative, or at one of these points it is. We're going to kind of go through and we're going to do the whole, like, figure out what all of these are because we can. By the way, this is number 2 on page 115. So what is the first thing that you would kind of do while like setting up this problem?
I would probably draw the tangent lines for all the points.
That's a good place to be. So there is something there. I'm going to try to make these be in different colors. Okay. So it probably looks something like that. Next, like, what would you do?
One of these points are going everywhere. They're both negative. Well, we know D is a 0, so that would rule out where like the positive. C is positive. B is positive. So then it would leave A and E as negative. I just work from the most obvious down to where it gets like more difficult sometimes to differentiate.
Yep, that's a good plan. So first things, I would try to figure out exactly where the first derivative is positive and negative, which is exactly what you did. So you said that the first derivative was positive at what point? C and point B, right?
Yeah.
And then it is negative at point A and point E. And then we have point D where it's 0. So the first step to solving this problem is figuring out what the first derivative is in all of these like places. And then the second step of the problem is we are interested in particular in where the first derivative less than zero, where the first derivative is less than 0, so where it's negative. So compare points A and points E. What's happening at each of these points?
At A, it's concave up decreasing, and then at E, it's concave down decreasing.
Okay. What happens if x increases on A? What happens if the function continues like this? To the derivative. What is the derivative at this point right here?
0.
Yeah. So the derivative here
Mhm.
is approaching 0. This is f, we'll call it df dx, is approaching 0 at that point. And then for e, what happens around e? We said it was concave down. As x increases, what happens here?
It's approaching 0.
Is it approaching 0 as x increases?
Well, from what they give you, it looks like it's decreasing until.
Yeah, so the derivative of the function gets more negative as x increases, right? So the further we go along this function, the more negative it's going to get.
Mm-hmm.
Like you would have at this point, something that looked maybe like this instead, so more negative derivative. Okay. So which of these points has a second derivative that is negative?
E.
Yeah. So we know that when df dx is less than 0, we have something that is concave down. And it kind of makes sense as we're like looking at this graph, because when we are sitting in this peach at point A, our derivative is approaching 0. So our derivative is becoming less and less negative, which indicates that our second derivative is going to be positive. Because it's, sorry, we were talking about this in the other calculus class too, in terms of like physics. And like if you throw a ball like straight up in the air, right?
Mm-hmm.
It's kind of like how like you can envision it. If you throw a ball like all the way up, it's moving up, but the force of gravity is always pulling it down.
Mm-hmm.
Right? So in the case of this like second derivative here, the second derivative, it's positive at point A, so it's tending it towards 0. So the derivative is increasing, like the value of the derivative is increasing in this area. So those are like different kind of ways that you can like look at a graph and kind of interpret. But the easiest way, obviously, is recognizing that concave up indicates that your second derivative is going to be positive, and concave down indicates that your second derivative is going to be negative. Where is the second derivative 0?
Second derivative is 0 is at D.
Is it? Just because the derivative is 0 does not mean that the second derivative is also 0. So the place at which the second derivative is going to equal 0, which we'll call this, is where it moves from being concave up to concave down.
I was going to say, would it be points of inflection then?
Yes, exactly. So it's the inflection point that is right between B and C. And so right here is where that is. Okie doke. Let's take a look at some more problems. For problems 4 through 9, they want you to give the signs of the first and second derivatives for each of the functions. Each derivative is either positive everywhere, 0 everywhere, or negative everywhere. Okie doke. So there are a variety of ways to kind of approach these. I'm going to draw out a couple of these graphs. We're just going to do 4, 5, and 6. 4, 5, 6. And so 5 is the straight line. 4 looks like this. And 6 looks like this. All right. So what's up here? What's going on with number 4?
It's increasing its concave up.
Mm-hmm. So that would mean what?
Hold on. Each derivative is positive everywhere.
Mm-hmm. So is not equal to is greater than 0, increasing as we said on x. And this is greater than 0, and we called that because it's concave up. Exactly. And another way of looking at this, as I kind of alluded to previously, is saying, like, here is the slope at this point, and then here is the slope at this point, and as x increases, the slope is increasing. Like the slope is increasing, so it's getting more and more positive, which would indicate a positive second derivative. So it's kind of looking at like the behavior of the slopes. Another way of looking at this would be to like draw the derivative, which would look very similar because this is an exponential function. But what about number 5?
5 is just constant.
Mm-hmm. So what is the first derivative?
Would it be 0?
Mm-hmm. Because m, the slope of this line
doesn't change.
Is constant. So what does that say about the second derivative?
Well, there's no concavity to the line, so it...
Yep. Another way of looking at that is if the second derivative is the rate of change of the first derivative, and the first derivative equals 0, for all numbers, in that case, the rate of change of 0 is also going to equal 0 on all numbers. Okay, and number 6, what are we thinking here?
Decreasing.
Okay, so that would mean the first derivative is...
Well, it's also a linear function, so it looks to be as x gets larger, y is decreasing at a constant rate.
Yeah, okay, so I'm going to go back and revise something that I said here. M is a constant 0 here. Right? So what would you call this first derivative? Is this greater than 0, less than 0, or equal to 0?
Less than?
And let's put a note down that m is constant, but it is negative, right? So we have this tangent line that would essentially like be this line, but it's always the same negative slope. The rate of change of this function is always going to be the same. What does that say about our second derivative then?
That it's going to be a constant negative because there's no concavity.
Well, if there's no concavity, what are we looking at?
The rate of change.
You said in this function that the second derivative was 0 because there was no concavity. What would make you saying, looking at this function and seeing no concavity, what is different between the two? So you said that this is less than 0.
Because it's decreasing at a constant rate. draw a tangent line, it's going to mirror the...
And that is a good explanation for the first derivative, which is the rate of change of the function, which is a constant negative slope. So what is the second derivative? So it's the rate of change of the rate of change of the function, right?
Mm-hmm.
So if the rate of change of the function, am I looking at like what is this going to be look like? This is just going to be some number, right? Some constant negative number.
Mm-hmm.
So if I have the rate of change of something that's not changing, what is this going to what is the second derivative going to be? Positive, negative, or zero?
You lost me.
Okay. So I'm going to erase some of this. So we are looking at this function, right? This function we know has a constant slope. And we know that, call it dy dx, is less than 0. And we know that it is a single number. In this case, I don't know, it might be like -1, -2, some constant number. But it is like definitively an integer. Mm-hmm. And dy dx is constant. Changing. So we've established that the second derivative is the rate of change of the first derivative, right?
Yeah.
So we're taking the rate of change. Basically, this question is saying, what is the rate of change of an unchanging number? And if it's not changing, that rate of change is going to be 0. Right?
Yeah. Because it would be, constant.
Mm-hmm. Okay. So what's different here? And you were right when you said that over here, you said this has no concavity. So graphically speaking, there's no second derivative, mm-hmm. right?
Yeah.
So you were right when you said that. The difference between these here is that here, m is a constant number that is equal to 0. So m equals 0 at all x. And here, m does not equal 0 at all x. M equals -1 or -2 or some negative number. Does that kind of make sense? Like what is different between these two?
Yeah, because when it's a straight line across and there is no tilt or angle or slope to it, it's 0. But then even though it's a linear function, if it's angled, it's a constant rate of either increase or decrease.
Exactly. So another way that we can check this is I'm going to draw the derivatives. Like we did this last week, right? Where we were sketching out derivatives.
Yeah.
So for this one, the derivative for number 5 looks like what?
It's just 0. I mean,
mm-hmm. It's a flat line right at 0 because it's 0 throughout.
Yeah.
What about for number 6?
Great. I'm still working on this one. Like I said, I've had a rough week.
Nope, you're good.
Give me a hint real quick to get my thought going.
Okay. So if we have a constant slope that is less than 0, we said that it's going to be like -1 or -2 or something like that.
Yeah.
Then it's just going to be one single number, a flat line. The derivative is going to be the same number at all points on the line, right?
Okay. Yeah.
Because m at this point, we'll call it -1. All right. So m at this point equals -1. So the derivative equals -1 at like this point. And then m at this point, m equals -1. And then at this point, m equals -1. So for all points, the slope is going to be -1. And so if we're graphing the slope, then that's just a flat line right here at -1.
So because it's a decreasing at a constant rate, you would just draw a straight line, flat line below.
At whatever that rate is.
Yeah, at whatever. But because we don't know the rate, it would just be below 0.
Yeah.
Okay.
So now that we have that, how can we use this to find our second derivatives? Well, if this is df dx and the second derivative is equal to the derivative of the first derivative, then we can just look at the slope of this graph and just treat this like we would like any other, like if we were trying to find a regular derivative. We would say that here the slope is equal to 0 of this function. So the slope is equal to 0 and it's constantly 0. So we could say that the second derivative of the function is equal to 0 because we have this flat line that is representing the derivative function. So if you look at them as like nested like this, then that's another way of kind of approaching it, and you don't have to think about it in like concavity terms. So if we do this function here, we have this m is non-equal to 0 function up here, and then down here we have a different function that is the derivative. This is dy dx, and we can just take a look at this function to tell us what d squared y dx squared is. So what is the derivative of this function down here?
-1.
What is the derivative of it though? That's what its y value is equal to. But what is the slope?
0.
Yep. And so that's our answer again. Does that kind of make a little bit more sense?
Yeah, it's getting there.
Where are you like at what point along this whole shindig is most uncomfortable for you?
What happens is I will understand it, and then I don't know, somewhere it just breaks and I get confused again. So I think it's just
okay.
practice.
All right. Okay.
Because if I could identify the break, I would totally work on that weakness. But it's like I'll be doing the problems, and it's like I guess I can just logic it out, like especially when it's cost and revenue, and the knowledge of how it works. And I can figure out how and like the mathematical rules, and I just get the answers. But like when we're talking here, it's just like I lose it.
Okay. Let's take a look at problem 16 real quick.
Okay.
So we are going to be on page 116. We have values of f of t in the table. And oh, that's not right. 4, 6, 8, 10. this is real bad. Okay. Sorry, I'm going to have to add another tab in here, which is very annoying. I just want to be able to like have the numbers in an area that I can work with them pretty easily. Okay. So that's 122. Okay. So we have this table here that we're going to pretend is, are you kidding me? Okay, never mind. Zoom hates me, I guess, and that's just what we're gonna do. Okay, so the numbers that you can see in your book.
Yeah.
Does this function appear to have a positive or negative first derivative?
First, well, let me sketch it out real quick because I know it increases until it gets between 6 and 8, and then it starts decreasing.
Are you sure? The first derivative.
All right, I'm totally
just check to make sure you're on problem 16 and not one of like the other ones.
Yeah, because it goes 0, 2, 4, 6, 8, 10 for t, and then the f of t is 150, 145.
Yep.
Okay.
So, first derivative. It's going to be positive, negative, 0 for the whole thing.
Well, they're all positive because they're all above 0.
Okay, so this graph here, or these numbers are for the original function. So
Okay.
what am I looking for if I'm asking for the first derivative? Like, what is the first derivative?
The slope, the instantaneous rate of change at the point.
Yep. So instantaneous rate of change. So is this changing? What is the rate of change of this? Is it changing in a positive or negative manner? As t is increasing, what is happening to f of t?
Oh, wait. I was looking at it wrong. Decreasing, my bad.
Yep.
I'm sorry. I still have remnants.
No, you're good. So if we started off at 0, we're at 150. At 2, we're at 145. At 4, we're at 137. At 6, we're at 122. At 8, we're at 98. And at 10, we're at 56. So we have something that looks kind of like this.
Yeah. Sorry about that.
Nope, you're good. So we know that the rate of change slash, like the initial rate of change slash df dt is negative. So what about the second derivative?
It would also be negative because it's decreasing concave down.
Yes. So that's one way to check this out is to sketch something out. So you can see how the slope is getting more and more negative. Another way to look is to see how big the gaps between these are. So we're changing here, the slope is going to be equal to 145 minus 150 over 2, which is going to be 2.5, right?
Mm-hmm.
So m is going to be equal to 2.5, or negative 2.5. And then I'll just pick out right here, this is going to be equal to negative 24 over 2. So this is going to be m is equal to negative 12. So you can just kind of pick points and compare. And it's easy to see that you're moving from like the gap between 0 and 2 is a gap of like 5 on the y like axis. The gap between 8 and 10 is a gap of like 40 on the y axis. And so you can see that the y is changing faster as the x increases, which is indicative of becoming more negative. So that's our negative second derivative. Okay, so now we need to estimate f prime of 2 and f prime of 8. So how are we going to do that? How are we going to estimate this?
Grab a point next to it and calculate the continuous rate of change?
Yep. So this kind of is a flashback to what we were doing a little bit earlier. We can estimate the instantaneous rate of change with an average rate of change. And so we're going to use the average rate of change from between these 2 points, right?
Mm-hmm.
Between 0 and 2, and then between 2 and 4, to kind of get a good idea of what's going on here. So this is going to be 137 minus 145. So 358, negative 8 over 2, which is going to be negative 4. And then let's also do between, because we're focusing on 2 and 8. This is a difference of, so it'll be 56 minus 98, 40, this is 42, right? So this will be negative 21. And this is the average rate of change. Negative 12. What I would do is I would just average these together to find the best representative at 0.2. So like at 0.2, from 0 to 2, the rate of change is approximately negative 2.5. From 2 to 4, it is approximately negative 4. And we average them together to get 3.25. Or just estimated rate of change. And I would say that is good enough for government work and call that a day. So yeah, do you have any questions about this problem?
No, I get that one. Now to find like the estimated rate of change, you just grab 2 on either side, the less than and the greater than, and then you just slope it and average it.
Yep. If they ever ask you to estimate something, it's just like use your average rates of change to get as close as you can. And that should be good for an answer. Let's move on to section 2.5. So this is applying, unless you have any questions about second derivatives.
No, it's becoming a little more clear, so it's good.
Good, good. Okay. So, so this is page 122. And this looks like a Q and not a G up here, but that's fine. So let's start. Let's do number 2 real quick. And then let's also do number 4. Okay, so in number 2, the function C of Q gives the cost in dollars to produce Q barrels of olive oil. So what are the units of the marginal cost?
The units would be dollars per barrel.
Mm-hmm.
Yeah.
And what is the practical meaning of this statement? Marginal cost equals 3 for Q is equal to 100.
The marginal cost to produce 100 is $3 per barrel.
Yeah. What is marginal cost in other words?
Isn't marginal cost the cost that's required to produce one more unit?
Mm-hmm.
One additional unit.
So the cost of producing 101 units will be how much more than the cost of producing 100?
$3 more.
Yep, exactly. And just to make this like explicitly clear, that means that C prime of Q is equal to the marginal cost. So how it's changing at the point Q is equal to 100 is given by C prime of Q and by marginal cost, because they're one and the same. Okay, so for number 4, we are given this sketch, and it asks us, is the marginal cost greater at Q is equal to 5 or at Q is equal to 30? And then compare and explain.
Is this, as I understand this question, because we know the wording, this is just eyeballing it off the graph they give us in the book, right?
Yes. So first things first, I would pick out exactly what points we're looking at. So here is 5, and we're comparing it to 30. Which is like right here-ish. Which has the higher marginal cost?
30.
Why is that?
Because when you find, hold on, I just lost it there.
So what is marginal cost? What did we say marginal cost was over here?
It's the derivative.
Yeah.
So it's the slope of the tangent line.
Yeah. So at which point is the slope of the tangent line going to be greater?
Oh, okay. At 5.
Yep. So Q is equal to 5. The marginal cost is higher. What does that mean? Would it be more financially responsible to move from 5 to 6 barrels or from 30 to 31 barrels of olive oil, if this was an olive oil graph?
31.
Yes, because it has a lower marginal cost. Okay, so let's do the exact same thing, but with, if I can get my eraser to work, which I guess I can't. Let's try it with Q is equal to 20 versus Q is equal to 40. So here's 20 and here's 40. Which do you think has the higher marginal cost?
40.
Mm-hmm. And that's just because it has the larger slope. This is like 0-ish. Okay. Let's try.
Hold on a sec. Sorry.
No, you're good. Sketch out this next problem. Okay. I'm going to go ahead and just sketch out this next problem. We're going to try to do problem 12. So this is page 123. And we have a graph that looks like this. running out of space on my tablet. So this is kind of a sloppy looking graph, but that's kind of what it looks like. Where this is a cost function and this is a revenue function. So given that we have the cost and revenue functions, this is for a charter bus company, we're asked to figure out whether the company should add a 50th bus or a 90th bus. And so basically how this problem is going to work is we need to compare cost and revenue in order to see if we make a profit. So if we said that profit is going to be equal to the costs or the revenue that we make from selling a product minus the costs of producing that product, then we can say that P of Q is equal to R of Q minus C of Q. Another way that we could put that is if R of Q is greater than C of Q, then we are making a profit. And if it's less than C of Q, then we aren't making a profit. So just becoming a little bit like more familiar with exactly which functions. I'm going to redraw C of Q so it looks a little bit better and a little bit like more accurate to what the book seems to have been implying, because it hugs this a little tighter, I think. So, and then this is pretty high up. Okay. So we are basically going to be looking at where are we making a profit and where are we not making a profit. So areas where we are not making a profit are here and here, because in these areas, the cost is higher than the revenue, right?
Yeah. Can you hear me?
Yes, I can hear you. So with a cost higher than revenue, we're not making a profit in those areas. And from here to here, we are making a profit.
Mm-hmm.
So it's important just like walking into this, understanding where we are making a profit, where we're not, and the points at which that changes. So, and that's all going to feed into our answer of whether or not we should get this 50th bus. So if 50 is at this point right here, and the line moves up, what we need to consider is what is the cost of, or moving from 50 or 49 to 50 buses. How are we going to compare that?
Calculate the slope between 49 and 50 and then use that difference to estimate between 50 and 51.
Well, we don't
just by eyeballing the graph. You want a 51st bus, but you don't want a 91st bus, because right there, that's where it's kind of like the break-even point and you're going to lose money.
Well, the breaking point is at closer to like 103. And so that's not quite the reasoning. The idea is that if profit is equal to revenue minus cost, right,
Mm-hmm.
then we're going to call this marginal profit. Like the change in profit from moving from 49 to 50 buses is going to be
Mm-hmm.
equal to the marginal revenue minus the marginal cost. So if the marginal revenue is greater than the marginal cost, then we should
Add the bus.
Because we would be making more profit. Our profit would increase moving from 49 to 50. So instead of looking at exactly where we're making profit on this graph and where we're not making profit, we're going to look at the marginal revenue and marginal costs. So what is the marginal revenue? R prime of Q.
Mm-hmm.
We can figure that out based on the numbering of the graph. Right? We can just find the slope of that line.
Mm-hmm.
So what do you think that would be?
I'm just figuring it out real quick because I know it's a straight line. I'm just doing the math.
Yep.
This is slope of 4.
Is it a slope of 4? I got a slope of 8.
Oh, I could have done it back. Hold on. I may have written it backwards because I'm trying to do it really quick.
Nope, you're fine. So basically, I just looked at that first square, and I said my delta y is equal to 200.
Mm-hmm.
My delta x is equal to 25.
Mm-hmm.
And so 25 divided by,
Oh, okay. Never
or
mind.
200 divided by 25 is going to be 8.
Yeah, you're right.
So I just thought that first box was the easiest because I had 2 zeros that I could work with. So we know that the R prime of Q, which is equal to the marginal revenue, is going to be 8. And I've always been made slightly uncomfortable by writing down MR instead of R prime of Q because I feel like it takes the Q out of the question, you know? Because if you write down MR, you're not really thinking about like this is like a derivative and how it's changing, but it's always changing with respect to like how Q changes. Okay, so what about C prime of Q? A little less easy to estimate, but at 50, is C prime of Q less than or greater to R prime of Q? And I can go ahead and sketch a tangent line. Something that looks like that.
The slope of the tangent line looks less than the slope of the revenue line.
Yes. So should we add a bus?
Yes.
Exactly. We should add a bus because our marginal revenue is greater than our marginal cost. So what about at 90? So that's up here-ish. Should we add a 90th bus?
Yes, you can still add a 90th bus because it's still less than the cost function.
Is it less than?
Well, it's kind of mirroring it, and it looks like eventually, as you try and add more buses, they're going to eventually intersect.
Yeah. What is that, like if I had a line that looks like this, and this line in purple, I'm just going to extend it. What does that mean about the slope of the line that's in green?
It's more rapidly approaching the cost function.
It's not rapidly approaching the cost function.
Or there's less marginal revenue? No.
The marginal revenue is going to stay the same because it's a line, right? Okay. So the marginal revenue is always going to be 8. No matter how many buses we have, if we add another bus, we're always going to get 8 more.
Okay.
Whatever. This is measuring dollars, millions of dollars, I don't know. But the question is whether this green line has a slope that is greater than the slope of the tangent line to R, which is R. Right? So the rate of change of R is this purple line.
Yeah.
Because the slope is going to be 8 everywhere. And then the tangent line to C of Q is in this green. and that is going to represent the marginal cost. And here in the purple, we have the marginal revenue that we can kind of outline. So is the marginal cost at 0.90 greater than the marginal revenue? What is the slope of this line of marginal cost? Is it greater than or less than the slope of the line of the marginal revenue?
Well, when you extend it, it's greater than.
Yeah, well, it's going to be greater than regardless. It's not about whether or not I extended it or not. I just extended it so that you could see them intersecting and you could see that the marginal cost was greater. But even if I didn't intersect them, the marginal cost is still going to be greater. And it partially is due to the way that I drew this graph. But if you look in your book, the line is pretty.
Yeah, I can kind of see it where, like, if I draw it in the book. Yeah.
So if the marginal revenue is less than the marginal cost, then do we get another bus?
No.
Yeah. So because it would reduce our profit. Well, it wouldn't. Yes, it would. It would have a negative impact on our profit. The cost of adding that extra bus would be too much. Does that all make sense?
Yeah.
Okay. I really want to get to the focus on theory.
Okay.
So let's review problems, not the focus on theory. There is, okay. All right. So do you have any other questions about the marginal cost revenue experience?
No.
Okay. So now finding derivatives by hand. So this whole focus on theory, I don't know if you've looked through it yet. It's pretty dense in that it uses limits in a way that we don't usually, like we haven't really touched on limits in this class. In the other calc class that I teach, limits are like the very first thing that we pick up on because of this definition of a derivative. So we think about limits as if we're trying to, like, we're looking at a function and we want to see how it behaves in like the long term, or how it behaves as it's like coming up on a certain like value of x. And so in this, we talk about like limits, we talk a little bit about continuity, and then finding derivatives by hand, which is using the definition of a limit to calculate derivatives. So I am going to start with number 1 or number 2, whatever graph you think looks nicer. It's both the same problem, so you can pick whatever graph you want to do. But
we can do number 2.
Okay. So
I'm just sketching it.
Sorry, I'm trying to get decent looking.
You're fine.
So it looks something like that.
Mm-hmm.
Draw out this a bit straighter. Okay. All right. So we get to label a variety of different points on this graph as we're using it to calculate the derivative by hand. So it's given to us that we have this point like right here that is A, right? And so mark lengths and represent the quantities in parts A through E, and pick any H with H greater than 0. So what is the first thing that I'm going to do for parts A and B?
Pick another H that's greater than, another point on the x-axis and label it as H, probably greater than A you usually go.
So we'll have this point that we'll call h. And now I have two lengths here, right? I have this length from here to here, and then this length from here to here. What is the bottom one?
The bigger one is a plus h.
Mm-hmm. So I'm going to recolor that, maybe. I'm going to recolor that in a color that is easier to tell apart. And so this is a plus h. And then in the orange here, this is the distance h. So this is not the point h, but rather the point a plus h. Right? Okay. So now we have this distance h. We have the distance a plus h. Now what point is f of a? How am I going to find that?
Isn't that where you draw the dashed line up until it hits the function and that would be f of a?
Yep. So this is just the y value of the function. So if I had a function that was f of x, that is this function that we can see here, then if I put a number in a, like if, for instance, I could sub in the number 2 for x, right? Mm-hmm. So if a was equal to 2, then I would, just get a y output. So in this case, I've got f of a. And so that's at this point in the red. And then I'm also going to find f of a plus h, which is the exact same thing in that here is the point. I moved it a little bit to the left. So instead of moving that, because it's going to be harder to erase, I'm just going to scoot over my h plus a a little bit. So, all right. Okay, so we have this. Okay. All right then. Now we need to represent f of a plus h minus f of a.
Okay, so isn't that just drawing a line between the 2 points and finding the slope?
That's in essence what we're doing here. That is like what we're doing here. But specifically asking us to find the f, this distance here, this is f of a plus h, or h, the difference between f of a plus h and f of a, right? So this is going to be a negative number. So it's like moving like down like that. So that's this distance here. So this is the vertical change.
Mm-hmm.
And now we also have, I'm going to outline the horizontal change that we have.
Mm-hmm.
And so that is going to allow us to find the slope between these 2 points. And so this is f of a plus h minus f of a over h. Delta y over delta x. Right?
Yeah.
So basically what we did here is we have an average rate of change in that we are moving, we know it's going to be negative. We know this number will be negative because f of a is greater than f of a plus h. And that makes sense because as x increases, we're moving down. And yeah, so these are all of the parts A through F, marking like on the graph where things are.
The only thing that threw me off the first time I did this before I looked at the answer was that A plus H is the whole value
Mm-hmm.
from 0 up to h.
Okay, that's
First, I thought it
the
was
issue.
just, huh?
That's the issue. I also, when I first wrote this down, just wrote h as a point, but this point is a plus h, right?
Yeah.
This is not point h. H is always going to be a distance.
Okay.
So this is point a plus h. And this, I'm going to change up my coloring a little bit here. This point is, this is a plus h. So the distance from 0 to here is going to be a plus h, because it's a plus h minus 0. And then this distance between the points is going to be h. And so that's how you get, like, if this is the distance a.
Okay, now I get it, because a is the distance from between 0 and a.
Exactly.
Okay, now I get it. Thank you.
So, so what the goal ultimately here is we want h to get really, really small. And I think we discussed this like earlier in the class, how we were ultimately going to approach this with the goal of making a very, very small h to get a better and better approximation of what is actually happening, right? Mm-hmm. Because we can pretty clearly see that, sorry, I'm going to clear this out a little bit so that I can draw what I want to draw in peace. If I have a is here, actually I'm going to move a little bit too. So if I have a is here, right? And I have an h or an a plus h1 here, and I have an a plus h2 here. I can draw the line between these. And this line that I've drawn represents an average rate of change from between these points, correct? Mm-hmm. Which is the better approximation of the graph? Which is like a better description of what's happening to the graph?
Hold on. Sorry. H plus 1.
Yep. So now if I'm going to add a plus h3 here, now which is the best approximation of the graph?
A plus h3.
Yep. And the goal is to make h as close. I am still on a line. So this is a plus h4. We want h to be as close as it can possibly be to a, so that it can line up as best it can with the function at hand. So that's the ultimate goal of this, right? Mm-hmm. Is to like get this to be like as best a representation as possible. And so that's the goal of the derivative. And now you know how to calculate that by hand by using the a plus h, which we will do in problem. Do they not make you do this? Oh, they do. Problem like 34 through 43 is when they have you do this. So we're going to kind of start a little bit earlier in that we are going to work through some of these limit problems first. Okay. But yes. So for problem 3, we have e to the 5h minus 1 over h. So they ask you, what is the result when we substitute in h is equal to 0?
Get 0 over 0.
the big thing is that we have a 0 in the denominator, and that's a big no-go. So we can think about what happens in the numerator, but the biggest thing here is that when we substitute h equals 0 in, we have a big fat 0 in the denominator, which is not okay. So we need to find out what happens when h is equal to 0.1, h is equal to 0.01, h is equal to 0.001, and h is equal to 0.0001. So that we can observe how the function behaves when it's not technically equal to 0, but is getting close to being equal to 0, if that makes sense.
Mm-hmm.
So, do you have a calculator on you, and do you want to trade off some of these?
Sure. I'll do the first two.
Okay, and I'll do the second two. Okay, okay.
Okay, for h equals 0.1, I got 6.48721.
And for this last one?
5.1271.
Okay. So we can see pretty clearly how we start off at like 6.48, and then we get to 5.1 by just adding another 0, and then we get to 5.01, and then finally we're at like 5.00.
Mm-hmm.
Use the results of part B to estimate the limit as h goes to 0. What do you think this limit is going to be?
Well, it's approaching 5. So
Yep.
is that all we do for that?
Yeah.
Okay.
So the question is, if we have this problem, the limit as h goes to 0 of e to the 5h minus 1 over h, as h goes to 0, this limit is equal to 5. Because as h is getting close to 0, this whole thing is getting close to 5. And so that's how we would write this.
Okay.
Okay.
So you would just figure out your answer on what data you had available. Okay. So it's just trending towards 5.
Yeah, so that is the way that you would find it, by like substituting in answers. There are like methods to solving limits. I don't know if you guys did this whole section, right?
Yeah.
But for 9 through 12, you're just substituting volume values. So you should be fine.
Okay.
So there aren't like other ways of solving like things for limits though. Okay, so let's do, before we wrap up, I really want to get to something like problem 34.
Okay.
Where we are given a function and asked to find the derivative of it. And it gives you what the derivative is, but let's do 34, and then we'll also do one that's a little bit more complex.
Okay.
The definition of a derivative is going to be the limit as h goes to 0 of the function x plus h minus f of x over h. And that's going to be equal to some function or some number. And that is how we solve this. So if we have the function, in the case of 34, we have the function x, what, 5x we have?
Mm-hmm.
How am I going to set up this limit?
Well, for the first time, you put in isn't this where you do the composite and you would just put in 5 for x? 5 times 5.
Why would x be equal to 5?
Or would you just substitute in, because I didn't get to this part, like,
Nope, you're good.
5x. Would you do the simple substitution first?
Basically what we're going to do is we're going to say, if we have this function f of x is equal to 5x, right?
Mm-hmm.
If I were to put in f of 2, I would get 5 times 2. If I were to put in f of a, I would get 5 times a. Instead, I'm going to do f of x plus h, so I'm going to get 5 times x plus h. And so whatever's we're taking this function of, we're just going to put it into this function, and we're going to end up with 5 times x plus h. So that's our first part here, right? Minus f of x, which is equal to 5x over h. So I'm going to simplify this. I'm going to call it 5x plus 5h minus 5x over h. These x's are going to cross out, or 5x's, because we have a plus 5x and a minus 5x. So I'll end up with the limit as h goes to 0 of 5h over h. And then these h's are going to cancel out. So I'm going to end up with the limit as h goes to 0 of 5. And this is just going to be equal to 5. Because there is no h any longer in this function.
Okay.
Okay. And that's how we end up with this answer. They give you, as part of the question, they say that f prime of x is equal to 5. They just want you to be able to walk through the definition of a derivative to do it. So we're going to do it again. We can do, instead, let's do 38. And so here we have this function that is f of x is equal to x minus x squared. So how am I going to build this? Remember, if I have a function that looks like this, if I have f of a, I'm going to say that this is a minus a squared. I'm just going to substitute what's ever in here into the function. So how am I going to build this limit?
You're just going to substitute x minus x squared in?
So read to me what the function is. If I'm finding f of x plus h. First, step 1 is finding what f of x plus h is equal to.
So then wouldn't you multiply that by x minus x squared? Or isn't this the one where, no, that's when it's in the bottom. I'm drawing a blank.
Nope, you're okay. So whatever is in here, right? If this was a 2, we would just put, wherever there's an x, we would just put a 2. So instead of that, wherever there's an x, we're just going to put an x plus h. because it's whatever's in here. So we're going to end up with x plus h.
Okay.
So like one way to think about it is just like if this were an integer, what would I do with it? And so this is, again, if this were a 2, we would put 2 squared. Instead, we're going to have f of x plus h squared. And so we're going to put f of x plus h in here as x plus h minus x plus h squared minus f of x. And f of x is up here, x minus x squared all over h. Does that make sense?
It seems like something's backwards from what we've been doing.
This, if you haven't looked over this chapter yet, then it's not something that you've been doing.
I started the f of x plus h, but yeah. This is,
Yeah.
all right.
It seems counterintuitive to add more variables.
Yeah.
But remember that h is not really, h is being held constant. So whatever, like we can imagine that h is 1, we can imagine that h is like 4, it could be like 6.25. Like h is a number that is not like changing, like in this case in the blue, right? H only starts changing when we think about it in terms of a limit. And in that case, we're looking at it like a whole different scenario. So while you're thinking about f of x plus h, just think about like if I have something that's like a function f of x, then I can turn that into f of 2 or f of a or f of x plus h, because whatever is in here, I can just deposit into the function. So that's the easiest way I can tell you to think about it. In that, let's pretend that, for instance, when we were drawing that graph, we had h, and that was like this orange distance, and we weren't changing it. And we will be changing it eventually because we want to see what happens when we get really close to 0. But for now, just like think about it as like something that we're adding onto x to get that extra distance. And so we need to treat it like, this is wrong. I had the wrong place. My parentheses. Okay. So then our next step here is we need to expand this because we need to make this like a whole lot larger. So I'm going to end up with x plus h minus x plus h times x plus h is equal to x squared plus hx plus xh plus h squared. So this is x squared plus 2hx plus h squared, right?
Mm-hmm.
So I'll end up with x squared plus 2hx plus h squared minus x plus x squared over h. I can go ahead right now and I can cancel that x and that negative x. So now I'm looking at h minus x squared minus 2h x minus h squared plus x squared over h. And this limit is still here. I've just not like written it out because it's really cumbersome. So I have a plus x squared here, a minus x squared here. And so now I'm looking at the limit as h goes to 0 of h minus 2hx minus h squared over h. So I'm going to have this cancel with that h, and one of those h's. And so I'll end up with the limit as h goes to 0 of negative 2 x minus h. So I'm missing something somewhere. I dropped something. Yes, I dropped something somewhere. Sorry, this is why I have to write everything out.
No, it's fine.
So x plus h minus h plus x squared minus x minus x squared. Should be. Oh, it's very recent what I screwed up. This is 1 times h, right? And I can't just get rid of that h in its entirety. So yeah, that's where I screwed up. So I could rewrite this in saying this is h over h minus 2hx over h minus h squared over h. So this would turn into 1 minus 2x minus h. So if I have the limit as h goes to 0 of 1 minus 2x minus h, what is this limit equal to? And the way that we would solve this is we would just say, what if h equals 0?
Okay, so this I remember this part now. All right.
So if h equals 0, what is this equal to?
1 minus 2x.
Yep. There we go. Ta-da. Derivatives by hand. These can get really, really messy depending on what functions you're working with. So this is the only time you will ever have to do this, this section.
Can you do me a favor?
Yes.
And just neatly rewrite. So when we take, because I think I almost have it, the derivative by hand formula is the f of x plus h minus the f of x all over h.
Yep. The limit of that as h goes to 0.
Limit, yeah. H goes to 0. So then for this one, we don't even really have to worry about the first derivative. So then we took this. All right, I'll just work on the substitution. I thought I almost had it, but
yeah, basically wherever there's an x, you can just put an x plus h, and make sure that you treat it exactly like you would the regular x. Like we had that x squared here, so the whole thing gets squared, not just the x. But yeah, that's the gist of it.
Because I get plugging in the x minus for the subtraction, f minus x minus x squared. The one where I just went off the rails was the f of x plus h.
Yeah. Like I said, the way that you can do that is just first of all by practice. Yeah. But like if we were to have f of x plus h, or here, f of x is equal to, let me pick a function. I'm gonna flip to another section and just pick a function because I can't think of one right now.
That's fine, I know, I'll just practice.
Like if I had f of x is equal to 2e to the x plus x squared, what would f of x plus h be?
So everywhere there's an x, you would substitute x plus h. So it would be 2e to the x plus h plus x plus h squared.
Exactly. Exactly. So that is just the substitution there. You don't want to find that by hand.
No.
Finding anything by hand is rough. But this is the only section where you have to do that. So
I just understand where I'm losing the substitution in the first part. That's fine. Because as you can see, I know what it's just.
It's easy to get overwhelmed with this material. Do you have any more questions?
No, I'm good.
Okay. Then I'm going to let you go for the evening. I hope you have a wonderful evening / afternoon, etc. And I hope you have a good week. Just as always, email me if anything like doesn't make any sense during the week, and I'll make sure to cover it in the next week's session.
All right, thanks. Bye.
Thank you so much. Have a good one.